So in the second part of this segment, I'm going to elaborate on the weak localization phenomenon, and in particular I will discuss in more detail the self-crossing trajectories that are responsible for it, and in particular I will identify the physical circumstances under which they're actually important. And this discussion is going to be under the title I put here, Quantum Corrections to Diffusion. But before going back to these quantum corrections that we already mentioned in the previous video, let me remind you what classical diffusion actually is. Actually, the phenomenon of diffusion you can observe at home by performing a rather simple experiment. If you put a droplet of a dye in water and watch it spread out with time, so this evolution of this droplet, time evolution, spreading out of this droplet, is going to be described by the diffusion equation presented here with some diffusion coefficient d. So, but the phenomena of diffusion and the diffusion equation itself are, of course, much more general than this particular physical realization. And they happen whenever we have a large number of particles experiencing a random walk. So random walk is, if you can think about it as particle which moves every time step. It moves in a certain direction. It can go up, it can go right, it can go up, it can go down, it can go left, up, etc., etc. And so at each moment of time there is a probability, equal probability to go in any direction. And so if a lot of such particles are put together, they if you look at those particles from a large length scale, so their density, the evolution of their density is going to be described by this equation. And so here ρ is in general a function of a position and time. So how it is relevant to the previous discussion about electrons moving in the metal? So there, as we mentioned, so the disorders, some imperfections in the metal play the role of scatterers that somehow randomize the electron trajectories. And so we can think about electrons experiencing this random walk. And since there are many such electrons in a piece of metal, so if we want to describe their density, the density is going to follow the diffusion equation. So another interpretation of the diffusion equation is that this ρ is actually probability density of finding a particular random walking particle in a certain moment of time, at a certain moment of time, in a certain position in space. So there is a probabilistic interpretation of this equation if you want. Now, another comment I would like to make about this equation is that actually, in some sense, it looks similar to the Schrödinger equation in quantum mechanics. So if we were to put an imaginary constant I here, which we don't have to put, but if we were to imagine some imaginary time, so, and instead of the coefficient d, we would have had, let's say, minus h squared over 2m, then this equation would have become a free Schrödinger equation of a free particle for the wave function. So, so this is a purely mathematical analogy, I should say, but this mathematical analogy in certain cases actually goes a long way and allows us to calculate things that otherwise would have been very difficult to calculate. So at this stage, however, we don't want necessarily to involve this analogy. Instead, let me focus on the question of relevance to the phenomenon of weak localization that I mentioned, namely on the self-crossing trajectories. So, and here I'm talking about self-crossing trajectories of some diffusive particles. So let's say, so here actually what I mean is that there is some small length scale at which particle diffuses around, but as a result, in the realization of this random walk, it may lead to this self-crossing trajectory. And so from the perspective of this crossing point, what it actually means is that I'm asking the question of what is the probability for a particle to return to the same point where it started. So let's say I set an initial condition for my density at t equals 0 to be a delta function in space. So delta function, very sharply localized density in the vicinity of a particular point. Now, it turns out that one can actually solve exactly the diffusion equation with this initial condition. It's actually called the Green function. And this fundamental solution, the general solution to the diffusion equation, is written here. So here again, R denotes the coordinate in space, t is time, d is the diffusion coefficient, and this small d denotes the dimensionality of space. So it can be either one-dimensional space or three-dimensional space or two-dimensional space. And in order for us to find the probability to return to the origin, let's say we are looking for the probability of a self-crossing trajectory which starts from r equals 0 and goes back to r equals 0. So it means that we have to set r to 0 in this expression, or set exponential to 1, and that's what we're going to get for the probability of self-intersection. So again, what this guy implies is that if we take a random walking particles, put it by hand in the origin, and let it random walk, so this guy gives us the probability of it to return to the vicinity, the probability density more precisely, to return to the vicinity of this point in the time t. So now let us recall about why we were talking about these self-crossing trajectories. So the context in which they appeared was the diffusion of electrons in a metal, and we wanted to see, again, we wanted to find the probability for an electron to diffuse from an initial point to some final point, and there are many different trajectories that achieve that. So, and we focused on the quantum terms, the quantum interference terms, where different trajectories, L1 not equal to L2, would interfere with one another, and the interference term was this cosine of the difference in length between two given trajectories times p Fermi, the typical momentum of an electron, divided by h bar. And the statement was, unless L1 was actually equal to L2, this interference term would kill each other or average each other to 0, because you will get just a collection of positive and negative random numbers, and on the average you will get 0. But for the special kinds of terms where you can go clockwise or counterclockwise around a certain trajectory, this delta L here would be 0, and cosine of 0 is equal to 1, so we'll get a prescribed contribution from these guys. And so what we're trying to figure out now is how probable it is for us to actually get this self-crossing trajectory at all, and this is determined by this equation. But this guy tells us this probability density to return to an original point in a particular time t. While what we're interested in is any self-intersection. It doesn't have to occur necessarily in this particular time t. It has to occur at some point. So in order to calculate the total probability, which I will denote as p subtotal, I have to integrate this expression over time from some minimal t to some maximal t. So in here I should mention that I'm dropping the overall coefficients. I'm not keeping track of the coefficients. I'm just focusing on the most important terms. Now, the minimal time here is the minimal time that the diffusion equation is able to resolve. Being an approximation, it cannot describe the motion shorter in time than the consecutive collisions, let's say, of the electron between two impurities. So this guy is of the order tau, which was actually introduced in the beginning of the previous video. But I should mention that it's actually not important. What it actually is, it is only important that there is some cutoff. On the other hand, if there is no dephasing processes, if there is, the phase, quantum mechanical phase is perfectly preserved, then there is no maximum cutoff. So this guy actually goes to infinity, and therefore the integral that we actually have is an integral from some tau to infinity of dt t to the power d over 2. And this integral we can now easily calculate. And what is extremely important, what is crucial, is that this integral is finite if we are in three-dimensional space in which we live, but it's infinite. It's equal to infinity if we're in 1 or 2 dimensions. So physically, it implies the following: so that if we start, let's say, imagine you're in a spaceship and you're sort of flying around in completely random directions in 3 dimensions. So this result tells us that you're gonna be lost. You're never gonna return to the point where you started from. On the other hand, if you start walking around in a city, in a town, in a city you don't know, and you walk randomly long enough, you are actually guaranteed to return to the vicinity of the point where you started. From the point of view of the electrons, so this result implies that if we have a motion of electrons in 1 and 2 dimensions, so there will be an infinite number of self-crossing trajectories, and the probability of self-crossing is going to be equal to 1. So these terms are actually going to matter enormously at low temperatures, and they're going to blow up and lead to localization in low dimensions, and this is actually what happens. So if we now actually think about the physical consequences, of course, again, so this in principle, everything I'm talking about here is a rather complicated theory, so if we were to study it in full details, but I just basically want to maybe I will leave this result here. The total probability of self-intersection is really the key. The reason for this video is just to give you this result. Essentially, what it tells us in conjunction with the path integral argument and some intuitive arguments is that in low dimensions the electrons are going to get localized at low temperatures. They're going to tend to return to the same point, and this localization is going to be a consequence of the wave nature of particles. From the experimental point of view, what it actually means is that if you perform a measurement of, let's say, resistance, which is 1 over conductivity as a function of temperature, so at high temperature where various effects disturb the phase, so this quantum interference phenomena are basically unimportant. Whether or not the trajectories cross or not doesn't play any role. So you will have some resistance and it will slowly actually decrease, but then at some point it will actually shoot up and become an insulator. Now in this qualitative curve, so this part of the curve corresponds to the weak localization phenomenon that we have been discussing, and this part is the classical Drude conductivity, which goes back to more than 100 years ago. So, and the prediction is that in 1 and 2 dimensions, per this argument, these quantum interference terms are going to take over and you're going to get an insulator, while in 3 dimensions, actually what's expected is that you're going to remain a metal and the resistivity is going to saturate in 3D to some finite value. And this is indeed what happens. So, and there do exist quasi 1-dimensional and quasi 2-dimensional materials, let's say nanowires in so-called semiconductor heterostructures, 2-dimensional films, where this behavior is observed. So I should emphasize again that the full theory of this localization is an extremely complicated theory, and we just got a flavor of it, so hopefully, but it's not the full story. And interestingly enough, what I told you about here, actually this weak localization is a precursor to a different phenomenon, which is actually called strong localization, for which Phil Anderson, professor emeritus at Princeton, got his Nobel Prize in 1977. So we obviously don't have time now to discuss in any detail this very interesting and complicated theory of Phil Anderson, but let me just mention that next week we're going to go back to standard quantum mechanics, and one problem we're going to solve is a particle in a potential well. And in this problem, we're going to see that the particle, when put in a potential well, gets localized by the well with some discrete energy levels. Not continuum of energy levels, but discrete levels. And so the essence of the theory of Anderson, if it can be summarized in a few seconds, is that in a random landscape of such a potential wells, so if this is, let's say, V of R, so the energy levels that electrons are going to acquire are not going to match each other. And so they're not going to be able to hop from well to well because of the energy conservation. And this would completely suppress conductivity, and this will lead to the strong localization. So that's the only thing I'm going to say. And next week we're going to study, actually we're going to study simpler phenomena using the Schrödinger formulation, in particular the appearance of such discrete energy levels.